In this video, I'd like to cover what I would like to accomplish in the next couple of days regarding the secondary, tertiary, and quaternary structures of protein, as well as the bonding between different strands of DNA, which are nucleic acids. What you should have with you, or should be able to attain, y lo voy a explicar todo en español también, así que todos pueden participar. I have this pipe cleaner. Tengo esta como hilo, no sé exactamente cuál es la palabra, pero tengo esto en verde, y también tengo estos para usar para pegar papeles, y tengo un papel que tiene todos esos ácidos aminos. So I also have, what I have are these pipe cleaners, paper clips, and then I have sheets, several sheets that show amino acids. Okay, so the first goal is to decide which amino acids are polar and which are non-polar. La primera meta es decidir cuáles de estos ácidos van a mezclar con agua que son polares o cuáles no van a mezclar con agua que no son polares. So what I can see, carbon-hydrogen bond, these are non-polar. Carbón con hidrógeno no es polar, así que what I can do is just label it NP, no polar, not polar. Valine also, hydrogen, carbon, carbon, hydrogen, carbon, hydrogens, not polar. Over here, again, this is the famous leucine from Jurassic Park, if you were really paying attention. Also non-polar. Now, amino acids do have one end that is polar. When they are floating around in liquid water, we have a hydrogen connected to, we have a nitrogen connected to hydrogens. Nitrogen is very electronegative, pulls the electrons. Here we do have a partly minus charge, partly plus charge. Over here, this is really, what this is really showing is a carbon double bonded to an oxygen. And again, we have a strong pull on the electrons here, strong pull on the electrons here, and then this is partially positive. Lo que tenemos en cada de esos ácidos aminos es nitrógeno, que es muy electronegativo, que está jalando los electrones más cerca, así que tiene una carga parcialmente negativa. Aquí hay una carga parcialmente positiva porque el hidrógeno no puede jalar tanto por los electrones. Here, same thing. Carbón está hablando, no está hablando tan fuerte, así que oxígeno tiene una carga parcialmente negativa y tiene una carga parcialmente positiva. This is the arrangement of all of the amino acids when they are mixed in water. However, when these become polypeptide chains, this OH comes off, this hydrogen comes off, the molecule is now more subject to what the functional group is instead of these bonds here. What these will do is form hydrogen bonds with each other to form a possible alpha helix or beta pleated sheet, but this won't really interact with water. It's a covalent bond. Lo que va a hacer es esta parte, oxígeno, hidrógeno, y este hidrógeno van a salir cuando se juntan más para formar una proteína. Así que no interactúan tanto con el agua, que eso es un enlace covalente. Lo que más importa cuando está conectado en una proteína son estos grupos que están conectados al ácido amino. All right, so I proceed through. This is definitely polar. Eso es un grupo polar porque oxígeno, hidrógeno. This looks very much like water, therefore it mixes nicely with water. And when this is part of a protein, this part is going to be attracted to water. It's going to be hydrophilic. Esa parte va a ser hidrofílico porque tiene esta parte que parece mucho al agua. Cysteine is special. So let me get my This is one of the ones that has sulfur. Now, is it slightly partially polar? Yeah. Slightly negative, slightly positive. Doesn't really mix so well with water, but this does something very special. This will form something called a disulfide bridge. If this comes in contact with another cysteine, what happens is these hydrogens get popped off, and the electron gets popped off, and then this sulfur will form a link with another sulfur anywhere in the molecule, which I'm hoping we'll be able to model here. Lo que puede pasar con este azufre es que sale el hidrógeno y puede conectar este ácido con otro en otra parte de la proteína, que espero que vamos a poder ver durante este proceso. So right now I will have to cut out. So anyway, we're going to continue. So this is really like more of a non-polar than a polar. It's kind of in the middle, polar, non-polar. Glycine, again, it's very small. I could call that non-polar. Isoleucine, definitely polar, non-polar. Carbons and hydrogens again. Just remember to look for these things. Carbons, hydrogens, carbon, hydrogens. Yes, there's a sulfur, but there's carbons and hydrogens. Not polar. No polar. Carbono, hidrógeno. Carbono, hidrógeno. Here we have a polar one, very polar. Oxygen and nitrogen. Aquí es muy polar. Oxígeno es muy electronegativo. Va a tener esa parte negativa, esa parte negativa, esa parte positiva. So that is very polar. That will mix with water. Eso es hidrofílico. Va a querer mezclar con el agua. Aquí otro polar al fin. Another polar one at the end. Now these are extremely non-polar. Now there is one nitrogen here, that's true, but all of this is carbons and hydrogens in a ring. Non-polar. All carbons and hydrogens in a ring. Non-polar. Carbons and hydrogens, non-polar. Carbons and hydrogens again. Non-polar. Here, yes, we have carbons and hydrogens, but remember, O is very electronegative. Hydrogen is not so electronegative, so this would be a polar one. Ese es polar porque esa parte parece el agua. Sí tiene carbono y hidrógeno, pero esta parte es muy polar. And then the last one here, again, that ring makes it look non-polar, but this does actually make it polar, because that is very symbolic of all polar compounds. Okay. Eso es, parece no polar porque tiene esos carbonos y hidrógenos, pero también tiene oxígeno y hidrógeno que lo hace polar. Okay. So once we've identified this, the same amino acids are on here. Now you remember, there are 20 amino acids in all. Hay 20 ácidos en total, pero solo vamos a fijar en estos. What you need to do for your activity is make 3 different, I'll make it 4 different polypeptides with 5 amino acids each. And then you will need to send me the pictures of your peptides, label them number 1, number 2, number 3, and number 4. You have to send them to me in order to be graded. Now this may spill over. I'm not expecting everything to be done today. You should at least be able to get 1 or 2 of these done today, however. And let me just look up the code for the class. So you will have to go to Remind, the Remind app, or remind.com, and you'll have to send me these pictures for grading. It's a little way of getting you to hopefully sign up once and for all for Remind and get into the habit of using it. You can see I'm at school making this video. So what we need, the information we need, if you're in Bio 1 and you generally meet during period 6, your class code is MEASTBU. If you're in Bio 1 and you normally meet for period 8, you're going to have to send it to MEASTBUR. Lo que me tienen que hacer en periodo 8, tienen que bajar este app, Remind, tienen que inscribirse y tienen que mandarme fotografías de 4 de las cosas que les voy a enseñar cómo hacer. El código para la clase tienen que inscribir, tienen que join, tienen que inscribir a esta clase y me van a mandar las fotos de lo que hacen para recibir crédito. Okay. So what we need to do, I said 5 amino acids. Those 5 amino acids are going to be connected with paper clips. Now I do want to do it so that my paper clips stay in position. But this is my polypeptide chain. We're going to go through dehydration synthesis, and we're going to have 5 amino acids linked together. If you remember, dehydration synthesis, we're taking out a water. On the acid side of an amino acid, we're taking out an oxygen and a hydrogen, and on the nitrogen side, we are taking out a hydrogen. Hydrogen plus oxygen, hydrogen gives you water. And then we form a covalent bond between the 2 molecules. So, to begin, here is a possible list of the amino acids. I labeled some of them already. Now, one of these polypeptides must have a disulfide, di-2-sulfide sulfur bridge, which means I cut out, let's say I take 2 of my cysteine. Cysteine has the sulfur that can make a disulfide bridge. So on one page, I've cut out 1 cysteine, and on another page, the second page here, I've cut out another cysteine. And remember, my molecule needs to have 5 polypeptides. I'm sorry, 5 amino acids in the polypeptide, but in one case, I'm going to want now this doesn't fit perfectly. I'm going to want this. Now I understand that this part would really be connected in a peptide bond. I cut off a hydrogen here, I cut off an OH here. This would be linked to the next amino acid with a carbon and an oxygen double bonded. So we would have a chain like that. We don't have to get super into all of that. Oops, and I actually need to do this the other way for my disulfide bridge. Así que para que vean, lo que tienen que hacer es coger el ácido amino que tiene azufre. Y lo que tienen que hacer es conectar 2 azufres en una de las proteínas. So I'm putting this upside down as it looks because this is the backbone of my molecule. This is where my peptide bond would form. And what I would need to do is have 2. Necesito 2 de esos que tienen azufre. Eso es la espina de la molécula. So, sulfur and hydrogen, sulfur and hydrogen. As I told you, there are certain enzymes which do the functions of things in our bodies, many important functions. They will chop off these hydrogens, and we have sulfur and sulfur. Esos 2 azufres hay que conectar. Now let me get my tape. And what we should see in one of the molecules you're going to share with me, a disulfide bridge. This is the tertiary structure of a protein. This part of the protein is now stuck. That's completely changed the shape of the protein. Lo que ha pasado es que tenemos dos ácidos aminos que están conectados por esos dos azufres. Se llama un enlace de dos azufres. This is very important. So at least one of your molecules needs to show that disulfide bridge. Now, of course, you need to fill in other amino acids. You need to make 5. Can you reuse some of the same amino acids? Absolutely. Can you do the same thing over and over again? No. But let me I'll get a threonine. Threonine, again, this is where my backbone is, the carbon and nitrogen. This is the functional group. That makes it hydrophilic. It likes water. So when this joins into the protein, it will actually be sticking out. Esta parte, la OH parece mucho a la molécula del agua, así que eso va a estar, si esa proteína estuviera en agua, lo que pasaría es que esa parte estaría en el agua. So what I was saying is this is the hydrophilic portion. If we imagine that our protein is in the water, this part is going to be on the outside trying to mix with the water because of that polar part. Now, let's say I take phenylalanine. Phenylalanine has this very large non-polar hydrophobic portion. Carbon, 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 hydrogen. Carbono y hidrógeno es muy hidrofóbico, así que no quiere mezclar con el agua. What would happen in this case is this part of the protein, this would be on the inside of the protein molecule, trying to avoid being with the water. Esa parte no quiere mezclar con el agua que está alrededor, porque eso es hidrofóbico. Now, one other amino acid, again, I just look, is it polar or is it non-polar? I choose one. In this case, I have asparagine, which is, again, very polar. Este ácido es muy polar, oxígeno, nitrógeno, que está en el grupo funcional. Remember, this would be connected in covalent bonds to the other amino acids. But I really want to focus on the functional groups. Will this portion mix with water? Of course. This would completely want to mix with water. And in this case, I've made my first protein. Very short polypeptide, actually. Okay? So we have the amino acids. We have a disulfide bridge. I have a hydrophilic amino acid pointing outward, mixing with water. Hydrophilic pointing outward, facing with water. Hydrophobic turning inward, because that one does not like to mix with the water that might be around this protein molecule. So that's one example. Now, I can just pop these off and do another one based on the same idea. Which ones are hydrophilic, which ones are hydrophobic. This controls the entire tertiary structure of a protein chain or a peptide chain, which is extremely important for everything in your body. As we said, a condition, a disease like Alzheimer's, is because this protein is now folding in the wrong way. In this particular case, we're going to look at another set of amino acids and decide what that shape should be. So I'll chop out an isoleucine. I'll chop out a serine. I will chop out tryptophan. This is in honor of Thanksgiving. This is supposedly the thing that turkey has that makes everyone sleepy. I'll chop out a leucine in honor of Jurassic Park because that was the amino acid that was supposed to keep the dinosaurs from escaping from the island. And then I will include valine, which is another non-polar amino acid. When I first make this structure, this is hydrophobic. So it probably would be on the inside of a protein molecule that is at least one that's mixing in water. So that will be turned inward. That will want to avoid the water surrounding the protein. This one, very hydrophilic, will want to be facing on the outside. Lo que dije es que eso es muy no polar. Carbón hidrógeno. No quiere mezclar con el agua que está fuera de la proteína. Así que eso va a ser por dentro. Pero este aquí quiere mezclar con el agua porque parece muy al agua porque tiene oxígeno y hidrógeno. So this is number 2 sticking out. Eso está hidrofílico, quiere mezclar con el agua. Here we have another hydrophobic, which means I actually need to turn it inward. I almost confused myself there. This is my backbone. I would turn this inward because it wants to avoid mixing with water. But it does like to be near isoleucine. Esos dos son no polares. Quieren estar juntos porque tienen las mismas fuerzas entre las moléculas. They have the same, what we would call intermolecular forces. Two nonpolar things will want to stick together. They're both hydrophobic. Tryptophan, again, yes, there's one nitrogen, but it's kind of shielded here. Fairly nonpolar, so this one will also turn inwards. Este también es muy no polar, va a estar por dentro porque no quiere mezclar con el agua, es hidrofóbico. And the last one, leucine, also is hydrophobic. So what will that do to the molecule? It'll turn the protein's shape differently. Notice this protein is very differently shaped. Esa proteína o esa polipéptido es muy diferente en su forma. So that would be a number 2 that you could show me. I want you to show me different mixtures of hydrophilic and hydrophobic. And remember, we need at least one disulfide bridge. So that is part of your assignment. And then there's also some paper and practice to do as well. But this assignment will be graded based on you submitting 4 polypeptides, each of them made of 5 amino acids. You submit them to me on paper, and I get to see each picture and grade it. Make sure your name is also on the picture, at least your first name, so that I know who I'm dealing with, or your initials. That would also be helpful. You don't have to give away too much information by just writing a first name on the picture. And looks like we're ready to go. Thank you. Así que tienen que someter, tienen que entregar 4 polipéptidos diferentes, de diferentes organizaciones, diciéndome cuál es hidrofóbico y cuál es hidrofílico. Los hidrofílicos van a estar mirando hacia afuera, los hidrofóbicos por dentro. Tienen que tener una conexión de 2 azufres, como enseñé en la última. Tienen que darme 4 formas diferentes, 4 arreglos diferentes de esas moléculas. Y tienen que entregarme esos a este código. Tienen que sacar la foto y mandarme eso a través de Remind. So I will be checking these. You'll have to submit these to Remind so that I'm able to grade you and put in the grades. Also, just so we're aware, not everyone has completed their CK12 assignments. I have not had a chance to grade them yet. That's a last warning because once the grades go in, they don't change. I need to make sure that you are able to prepare yourself for the upcoming test, which will come most likely within the week that we get back to school. We do have to talk about pH, acids and bases. We also have to talk about nucleic acids and their bonding. But I think for today we'll focus on the worksheet I gave. And actually, I'm thinking December 10th. I think that's a Tuesday. That would be our next F day. That will probably be our test. So we need to get ready for that. The CK12s are excellent practice for the test. So I will see you later.